All right, so let's go over the quiz, starting with problem 1. Find the domain of this function. When we were talking about domain, remember what we wanted to do was focus on where does the function have a problem. And this function has sort of two things that can give it a problem. One is that the denominator, it has a denominator, so when the denominator is 0, that's a problem. And I think, pretty much everyone saw that, right? We want to solve x plus 2 equals 0. So when x equals 2, we have a problem. So for our domain, x is not allowed to be negative 2, right? The other place that we could have a problem is if we took a square root of a negative. So what I wanted to do is figure out where the inside of the square root, 9 minus 5x, is not a problem, right? Is not negative. So we want to solve 9 minus 5x greater than or equal to 0. So if I subtract 9, I'll get negative 5x greater than or equal to negative 9. And then when I divide both sides by negative 5, the inequality changes directions, and I get that x is less than or equal to 9/5. So for my domain, I have sort of two things. X cannot be negative 2, and x has to be less than or equal to 9/5. Okay, so if I think of this as like being on a number line, if here is 9/5, I want things smaller than that, except when I hit negative 2, I don't want to include that number. Okay, so this is what it would look like on a number line. If I wanted to write that as an interval, I would say, okay, I have all the numbers going from negative infinity to negative 2, not including the negative 2. And then picking up at negative 2 again and going to 9/5. 9/5 is okay, so it gets a square bracket on it. Okay, any questions on that one? All right, we'll move on to number 2. Find the equation of the line between the 2 points. This one went fairly well, I think, for the class, so we're just going to rush through this. I start with the slope formula. So I look at the change in y over the change in x, and we get 11/2. So then using my point slope formula, y minus 4 equals 11/2 x minus 3. And a number of you left the equation like this, and it just said find an equation of a line, so this is fine. If we wanted to write it looking like a function in the slope-intercept form, we could distribute the 11/2 and then add 4 to both sides to solve for y. So 4 is 8/2. Negative 33/2 plus 8/2, I believe, is negative 25/2. Okay, problem 3. This one had a similar issue to problem 1, where we have to be careful about the domain, and we're not just throwing out a single number. Again, the inside of the log can't be 0 or negative, so I want to solve for where the inside, 2x plus 3, is strictly greater than 0. Right? So we subtract 3 and divide by 2. So we see that x has to be bigger than negative 3/2, so the domain is negative, the domain is negative 3/2 to infinity. Okay. And finally, find the equation of the line through a point that's parallel to this other line. So what I want to do is I want to start by looking at this line here. 4x minus 6y equals 3x plus 1. And I want to find the slope of that line. And I think that the easiest way to do that is to write it in slope-intercept form, right? Y equals mx plus b. So we'll subtract 4 from both sides. So negative 6y equals 3x minus 3, and then divide both sides by negative 6. So y equals negative 1/2 x plus 1/2. And I can see that the slope of this line is negative 1/2. So now we're saying find the equation of a line that goes through the point 4, 1, and that has slope negative 1/2. So using the point slope form of a line, y minus 1 equals negative 1/2 x minus 4. And this was an acceptable answer if you left it that way. If we want to solve for y, do a couple extra steps. Distribute that negative half. So minus a negative will become a positive. And then add 1 to both sides. So y equals negative 1/2 x plus 3. Okay, and that's the quiz. Any questions over the quiz? All right, then let's switch over and look at the review problems. Should we just go through these in order, or do you want to ask questions? And
Can we do them in order?
Yeah, all right, we'll just run through the whole thing in order. Okay, so for number 1, find the domain for the following functions. So let's treat these one at a time. The first one, I have a fraction, so there's no square root, no logs. The only thing I have to worry about is where the denominator is 0. So I want to solve 1 minus cosine x equals 0, and I want to throw out any solutions to that equation. Okay, so negative cosine x equals negative 1, so cosine x equals 1, so I'm solving this trig equation, and so I get x is cosine inverse of 1 plus 2k pi, or x is the opposite of cosine inverse of 1 plus 2k pi. Okay, cosine inverse of 1 is 0. Okay, and the opposite of 0 is also 0, so we just end up with x equals 2k pi, where k is any integer. Okay, so my domain is that x cannot be those values. Okay. For part B, I want to know where the inside of the square root is greater than or equal to 0. Okay, this one's a little bit more complicated because it's a quadratic. What I'm going to do is I'm first going to solve and find out where is x squared minus x minus 6 equal to 0. And I'll do that by factoring. So I can see, all right, when x minus 3 is 0, or when x plus 2 is 0, I will get a solution. So x could be 3 or negative 2. And then what I do is I say, all right, I'll plot those on a number line, and I'll figure out for each interval in between, is that going to make my inequality greater than or equal to 0 or not, right? So I'm just going to test something. If I test x equals negative 3 into my original inequality, I'll have negative 3 squared minus negative 3 minus 6. So that's 9 plus 3 minus 6, which is 6, and that is greater than or equal to 0, right? So this part here works. Okay. Let's test x equals 0, because that's in between negative 2 and 3. So then I get 0 minus 6 greater than or equal to 0. That's false. So I do not want that interval. And finally, let's test something bigger than 3, maybe x equals 4. Okay, so I get 4 squared minus 4 minus 6. And I think that comes out to 6. That is greater than or equal to 0. So that part's okay. Right? So then our domain is, I can see it as on a number line here. I'm going to go ahead and write it in interval notation. We can have negative infinity to negative 2. Negative 2 is okay. And also the numbers from 3 to infinity. Okay. For part C, for this last one, I have 2 square roots and a denominator. So I need to worry about all 3 of those things. Okay. So for the square root on top, I need to solve the inside of the square root. X has to be greater than or equal to 0. But that's already solved, so that's done. On the bottom, I need that the inside of the square root is greater than or equal to 0, but then I also don't want the denominator to be equal to 0. So I can sort of just handle those at once by just saying, all right, it can't be equal to 0, so it's just 9 minus x squared is strictly greater than 0. Okay, and I'm going to solve this the same way we did last one because it's a quadratic. I'm going to factor it and figure out where that's equal to 0. And then I'm going to test intervals. So let's test x equals negative 4 and see, does this make my inequality true, right? 9 minus negative 4 squared, is that greater than 0? Negative 4 squared is 16, so I have 9 minus 16. 9 minus 16 is negative 7. Negative 7 greater than 0 is false. So the numbers over here are no good. Okay. Let's test something between negative 3 and 3. The easy number there is 0. 9 minus 0 squared works. And finally, let's test something bigger than 3. Let's test x equals 4. So once again, I get a negative 7 greater than 0, which is false. Okay, so putting this together, I need my x values to be strictly greater than 0, or sorry, greater than or equal to 0, and then also less than 3. So my domain is from 0 to 3. I don't include the 3 because it'll give me a 0 in the denominator, but I do include the 0. Okay, should have left myself a little more room here, but that's number 1. All right, number 2, there are 2 different ways to go about solving exponential equations. There's like an easier way because I can write these both as a same base, right? A base of 5. The more challenging way, or not, I shouldn't say more challenging. There's a more robust way that always works, but it's a little bit more work. And I could just start by taking the natural log of both sides. In this case, though, because the left-hand side is already a base 5, I can rewrite the right-hand side as being a base 5. So we have 5 to the power of 1 minus 2x equals 5 to the power of negative 1. Since exponential functions are 1 to 1, I can just write the two exponents equal to each other. Or another way to think about that is we could take the log base 5 of both sides. And then the log and the exponential will cancel each other out. So we get 1 minus 2x equals negative 1. And then we just solve away. So I get x equals 1. Okay, let's take a look at number 3. For solving this trig equation, the key is going to be to start by getting the trig function by itself. So I'm going to add 1 to both sides. So 2 times the sine of 3x equals 1, divide by 2. So the sine of 3x equals 1/2. And now I want to get rid of the trig function, so I'm going to use the inverse. Right? So we're going to take inverse sine of both sides. So we're going to say, okay, 3x equals sine inverse of 1/2. Let me just compute out what this is, and then I'm going to rewrite my equation. Okay, so for sine inverse of 1/2, if you remember your unit circle or you remember your little table of values, then you could just write this down. For those of you who, you don't remember your unit circle or you just don't trust that you remember it right, okay, you can use your calculator to find, your values off the unit circle. Okay, so I want to take sine inverse of 1/2. Make sure you're in radians. And we take sine inverse of 1/2. And since I remember that that's going to be one of my special angles, I know that the angle is some fraction of pi. So when I get my answer, if you divide out that pi, you can see, oh, okay, it's this fraction of pi. If you don't recognize that as 1/6, you can just say convert to fraction. And I say, okay, it's 1/6 of pi. 1/6 of pi we usually write as pi over 6. Okay, so 3x is going to equal pi over 6 plus 2k pi, or 3x is going to equal pi minus pi over 6 plus 2k pi. Okay. Pi minus pi over 6 is 6 pi over 6 minus pi over 6, which gives me 5 pi over 6. Okay. So for each of these equations, I now continue solving. I'll divide by 3. So I get x equals pi over 18 plus 2/3 k pi. And for this next one, when I divide by 3, I'll get 5 pi over 18 plus 2/3 k pi. Okay, where k is any integer. Okay, does that make sense? Any questions so far? All right, feel free to slow me down if I'm
I
going too
actually do
quickly.
have one question.
Yeah,
So that one was for sine, but oh wait, the next one is never mind.
yeah. So we'll go through a cosine. And then we also have an example that's tangent, so we kind of have our bases covered there. Okay, so for the next one, I want to start by getting cosine by itself. When I look at this, I might recognize that I have, like, this cosine squared. It looks like a quadratic. You don't have to do this, but one technique that I know helps if solving this seems confusing is to just do a quick substitution, right? If I let y equal cosine x, then this looks like 2y squared minus 1 equals 0, and this is a more familiar way that we're used to seeing quadratics. So I can solve this either by factoring or by the square root method, right? So if I add 1 to both sides, I get 2y squared equals 1, y squared is 1/2, so y is the positive or negative square root of 1/2. Okay, and y is cosine x, so now I just do I replace it back. So we have cosine x equals the square root of 1/2. Now, if you're going to be using your calculator, square root of 1/2 is fine. If you're remembering values on the unit circle, we typically write this as, square root of 1 over square root of 2, right, or 1 over root 2. And then from pre-calculus, you usually have the denominator rationalized. So this would be like a root 2 over 2 if you multiply top and bottom by root 2. Okay, so if I have cosine x equals root 2 over 2, and I have cosine x equals negative root 2 over 2, I'm going to solve those two separately. So now we use the cosine inverse. So x is cosine inverse of root 2 over 2 plus 2k pi. Or it can be the opposite of that, right? So cosine inverse of root 2 over 2 is pi over 4. And I know I get a second set of solutions when I have the opposite of that. So with sine, we do pi minus the first solution. With cosine, it's just 0 minus the first solution, right? Or just the negative of the first solution. Okay. All right, now I'm going to solve cosine x equals negative root 2 over 2. So x is cosine inverse of negative root 2 over 2, which gives me, so the way that I think about this one, I think about the unit circle here. I mean, my reference angle, right? You know, if I think about root 2 over 2, I know I get a pi over 4, but cosine corresponds to x value. So if I get a negative value, it's going to be over here in the second quadrant. Okay, so I get a 3 pi over 4. And then again, my second set of solutions is the opposite of that, so negative 3 pi over 4. Okay. All right, so those are all of the solutions, right? And again, where k is any integer. Those are all of the solutions to our original equation. Okay. All right, now let's look at solving a tangent equation. Once again, it's just not a simple tangent. We've got other stuff going on. So you could start by saying, let y equal tangent x. So then this is going to look like 2y squared minus y equals 10. And I can see, okay, that's a quadratic. Let's get everything on one side equal to 0. Okay. And this solves by factoring, I think, without too much trouble. I think what I want to do, though, I'm just going to take this as an example, you know, this opportunity to say, how do I factor using the quadratic formula? Okay. So we could say, all right, the quadratic formula, if you have ax squared plus bx plus c equals 0, then x is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so in this case, I'm going to get y equals the opposite of b. The coefficient of my y term is -1, so the opposite of that is +1. And then I have -1 squared minus 4 times 2 times -10 all over 2 times 2. All right, so let's compute away. -1 squared is 1, minus a negative is plus. 4 times 2 is 8, times 10 is 80. 80 plus 1 is 81. The square root of 81 is 9. So when I add these, I'll get 10 fourths. When I subtract, 1 minus 9 is -8 fourths. 10 fourths I can simplify to 5 halves. -8 fourths I simplify to -2. Okay, so now we have, replacing y with tangent x, I have tangent x equals 5 halves, and then I have tangent x equals -2. Okay, so I'm going to use the inverse tangent now. This doesn't look like the result of one of my special angles. So I'm not going to be able to get this one from remembering the unit circle or looking it up, you know, or remembering my little table. I'm going to have to use my calculator to compute an exact value here. I'm sorry, I won't get an exact value. I'll get an approximation. Okay, so let's get out our calculator and say, what is inverse tangent of 5 halves? Oh, my calculator. There it is. right, can everyone see my calculator? Okay, good. So sorry, that's tangent. I want inverse tangent of 5/2. And I'll just write down the approximation, 1.1903. Okay, so x equals 1.1903 plus k times pi. You don't get a second set of solutions. You just get the plus k pi, and that covers everything. Okay. So then for the other one, x is inverse tangent of -2 plus k pi. That's negative 1.1071. Right, and again, plus the k pi, where k is any integer. All right, any questions over solving trig equations? I know that was a real sticky point when we were going through it last week. Okay, so next one, working with properties of logarithms, write this as a single logarithm. So what I want to do is use those rules that we had. This is maybe backwards from some of the examples we were doing in class, but it's the same set of rules, right? So I'll just maybe quickly write down what those are. Ln of a times b is ln of a plus ln of b. Ln of a divided by b is ln of a minus ln of b. And b times ln of a is ln of a to the power of b. Okay, so what I can do for each one of these is I can take the coefficient and bring it up as an exponent. So we can say, all right, this is going to be ln of x plus 1 cubed. And then you sort of have the choice here of whether or not you want to leave this as a negative or whether you want to write it as a positive and write this to a negative power. And they both get you to the same spot. Okay, and then I have ln of 2x all to the 4th power, and then minus ln of 5 minus x. Okay, so rather than do these next steps one at a time, I'm going to say, all right, well, the positive logs are added. The negative logs, right, the minus ln of b, that's just going to put that b in the denominator, right? So the negative logs are just going to put those terms in the denominator. So now I can write this as ln of x plus 1 cubed times 2x to the 4th. You can write that in parentheses to the 4th. I think maybe a more common way to write that would be as like a 16 times x to the 4th. It's a little less confusing. And then we have the 2x plus 2, and we have the 5 minus x in the denominator. Okay. Now, there is some simplifying that you can do here, because I could factor a 2 out, and then I'll have an x plus 1 factor, and well, then that will cancel with one of these x plus 1s in the numerator. But we have already accomplished our goal, right? We've written this as a single logarithm. So I'm just going to go ahead and stop here. Okay, so that's the Chapter 1 review stuff. Now let's get into some of the Chapter 2 stuff. Let's go ahead and evaluate some limits. What I'm going to do for every single limit problem is I'm going to start by trying direct substitution. Okay, so I'm going to have 4 squared minus 2 times 4 minus 8 over 7 times 4 minus 4 squared minus 12. In the numerator, I have 16 minus 8 minus 8. That gives me a 0. In the denominator, 7 times 4 is 28, minus 16 minus 12. 28 minus 16 minus 12 is 0. So we end up with 0 over 0. That tells me two things. First of all, that tells me that direct substitution does not work, so I need to, keep doing something else. But it also tells me when I plug 4 into the numerator, I get 0. That means that x minus 4 is a factor. So when I go to factor this thing, to get an x squared, I have to have an x. To get a negative 8, I have to multiply a negative 4 by a positive 2. So if it does factor, this is the only way it can factor, right? So I double check it. X squared plus 2x minus 4x gives me the negative 2x, and then negative 4 times 2 gives me the negative 8. So that is how it factors. Same thing with the denominator. We plugged in 4 and got 0, so I know that x minus 4 is a factor. Here we have a negative x squared, so I have to multiply my x by a negative x. And our constant is negative 12, so I have to multiply a negative 4 by a positive 3. So again, if it factors, this is the only way that it really can factor. I don't have another option. So let's go ahead and double check it. Negative x times positive x gives me negative x squared. Then I have negative x times negative 4, so that's plus 4x. And then x times 3 is a plus 3x. 4x plus 3x gives me 7x. And then negative 4 times a positive 3 gives me negative 12. So that's how it factors. So now we go ahead and cancel away our x minus 4 factors. So we have the limit as x approaches 4 of x plus 2 over negative x plus 3. And now on this limit, I can use direct substitution. And we get negative 6. Okay, I want just to make a comment here as we're going through this. First of all, it doesn't make sense to solve a limit problem without writing down limits. So if you didn't write down a limit before you got to your negative 6, that's going to be an issue. The second thing that I just want to comment is that x minus 4 times x plus 2 over x minus 4 times negative x plus 3 is not equal to x plus 2 over negative x plus 3. It works for every number except for 4. Okay, so that doesn't work when x is 4. So if I'm not working with a limit, then canceling these doesn't work. And the only number it doesn't work for is 4, but the very next thing I'm doing is I'm plugging 4 in. Okay, so without limits, this doesn't work. That's why we have limits. So when you're going through and you're showing this problem, you absolutely need to be writing down limits. Otherwise, what you're writing down doesn't really make sense. Okay, next problem. Once again, I'm going to start by trying direct substitution. My pen went crazy. Okay, so we're going to try direct substitution. So we plug in 3 squared plus 2 times 3 minus 15 over 3 squared plus 2 times 3 plus 10. So 3 squared is 9 plus 6, which is 15. Minus 15 gives me 0. In the bottom, I have 9 plus 6, which is 15, plus 10 is 25. 0 over 25 is 0, but that's not a 0 in the denominator. That's a legitimate number. So using direct substitution, I just get that this limit is equal to 0. And I'm done. Okay, so if you try direct substitution and you get a number out, then that's it, you're done. Okay, let's try direct substitution. Maybe it'll work really nicely again, but probably not. Okay, so plugging in negative 5. Negative 5 squared is 25, times 2 is 50. So I have 50 minus 55 plus 5, which will give me a 0. And the bottom, 25 times 3 is 75. Okay, 25 times negative 5 is a minus 125. 75 plus 50 is 125, so when I subtract, I get 0. Okay, so here's where I think that it is very helpful to notice that if negative 5 gives me a 0, that means negative 5 is a root. So x minus negative 5 or x plus 5 is a factor. So if I want to get a 2x squared, I have to multiply x by a 2x. And if I want to get a positive 5, I have to multiply a positive 5 by plus 1. So we double check. 2x times x is 2x squared, plus 10x plus 1x gives me the 11x, and then the 5. Okay. Same thing in the denominator. The negative 5 is a root, so x plus 5 is a factor. So to get a 3x squared, I have to multiply x by 3x. To get a 50, I have to multiply 5 by a positive 10. So I have 3x squared plus 15x plus 10x gives me the 25x, and then plus 50. Okay. So now we can cancel away these x plus 5 terms inside the limit. And we're left with 2x plus 1 in the numerator and a 3x plus 10 in the denominator. And now try direct substitution. So I get 2 times negative 5 plus 1 over 3 times negative 5 plus 10. So we have negative 10 plus 1 gives me a negative 9 up top. Negative 15 plus 10 is a negative 5 on the bottom. So we end up with a positive 9/5. Okay, so I like to rewrite my conclusion here. I don't think I did in the last one, but so our original limit is equal to 9/5. Okay. All right, another limit. So once again, we're going to try direct substitution. So I have negative 7 squared plus 3 times negative 7 minus 28 up top. 2 times negative 7 squared minus the opposite of 7 minus 105. Okay, so we have 49 minus 21 minus 28 up top. 21 and 28 gives me 49, so 49 minus 49 is 0. All right, on bottom we have 49 times 2, which is 98, minus a negative 7, so plus 7. 98 plus 7 is 105, minus 105 gives me a 0. Okay, so we have a similar situation to the last one. I plug in negative 7 and we get 0 over 0. So I'm not allowed to use direct substitution, but that also tells me that x plus 7 is a factor. Okay. So if I want to get an x squared, I have to multiply x by x. If I want to get a negative 28, I have to multiply a negative 7, or sorry, a positive 7 by a negative 4. Okay. X plus 7 is also a factor of the denominator. To get a 2x squared, I have to multiply x by 2x. To get a 105, I have to multiply a 7 by, I believe that's 15. I should double check, but I think 15. So now we double check. X times x gives me x squared. Plus 7x minus 4x will give me a 3x. And 7 times negative 4 is negative 28. In the denominator, we have negative 2x squared minus 15x plus 14x gives me a minus x. And 7 times negative 15 is a negative 105. So we're in good shape. We cancel the x plus 7s. So we get now the limit as x approaches negative 7 of x minus 4 over 2x minus 15. And now we use direct substitution. It will work this time. So I have negative 7 minus 4 over 2 times negative 7 minus 15. So in the numerator, I have negative 11. In the denominator, I have negative 14 minus 15, which is negative 29. So we have 11/29. Okay. Now, if you use your equals to mean equals and not just like the next thought that I have, I can follow my chain of equality back to the original problem, and you're okay like this. If you have a lot of like scratch work running around, right, then you probably want to summarize and say, okay, like we did in the last one, rewrite the limit equals, in this case, 11/29. Okay, a couple more limits. I think it's just two more, right? Yeah. All right, let's try direct substitution. So we have 5 minus -1 over -1 plus 1 squared. 5 minus -1 is 6. -1 plus 1 is 0. Squared is still 0. This one is different than the last view because I don't have 0 over 0. The 0 in the denominator means I'm not allowed to use direct substitution, but a non-zero number over 0 means that I have an infinite limit. Okay, so the way that we deal with infinite limits is a little bit different. I know my answer is going to be infinity, negative infinity, or does not exist. So I don't need to really worry about specific numbers. What I need to worry about is, do I get a positive, a negative, or a little bit of both? So what I'm going to do is look at the left hand and right hand limit separately. Okay, so if I look at the left hand limit, I know that it's going to be either equal to infinity or negative infinity. So again, I don't have to worry about computing a specific number. What I'm going to do then is just say, well, as I approach -1, think about being infinitely close to -1 but slightly smaller. What am I going to get? Well, in the numerator, if I plug in something close to -1, it'll be 5 plus something close to 1. So it's going to be about 6 or a positive. In the denominator, I'm going to have something close to -1, so I'm going to get close to 0 here. But if we're to the left of -1, when I add 1, it's still going to be negative. However, when I square a negative, it'll be positive. Okay, so I'm going to get a positive infinity. All right, now let's look at the limit from the right. We have a very similar situation. When I plug in something close to -1 in the numerator, it's going to be close to 6, which is positive. In the denominator, it's going to be close to 0, but if I'm to the right of -1 and I add 1, we're going to get a positive number. In this case, it doesn't really matter that much because a positive squared is positive and negative squared is positive. So the limit as x approaches -1 from the right of 5 minus x over x plus 1 squared is also positive infinity. And since the left and right limit match, crazy again. So since the left and right limits match, the limit as x approaches -1, 5 minus x over x plus 1 squared is equal to positive infinity. You can just also write infinity. Okay, let's look at 12. Try direct substitution. So we have 3 times 6 squared minus 17 times 6 minus 6 over 6 minus 6 squared. It's easy to see that the denominator is 0. The numerator, I would recommend plugging into your calculator, right? What we end up is 18 times 6 minus 17 times 6 minus 1 times 6, so 7. So 18 times 6 minus 18 times 6 will give me 0. However you want to compute that. So I do get a 0 over 0. So that means that x minus 6 is a factor. So I can write that as the limit as x approaches 6, x minus 6, and then when I factor it to get a 3x squared, I multiply by a 3x. To get a negative 6, I multiply a negative 6 by a positive 1. The denominator is already essentially factored. I can write this as x minus 6 times x minus 6, but it's already factored for me. I say, okay, great. Cancel the x minus 6 terms. So this is equal to the limit as x approaches 6 of 3x plus 1 over x minus 6. And now I try direct substitution like we normally do. And I get 3 times 6 plus 1 over 6 minus 6, which is 19 over 0. So I'm not allowed to do direct substitution here. What I have is an infinite limit. Okay, so I have an infinite limit again. So once again, I'm going to check the left and right-hand sides. So we're going to look at the limit as x approaches 6 from the left of 3x plus 1 over x minus 6. Okay, if I plug in something close to 6, we're going to have approximately 18 plus 1. That's like close to 19. That's a positive. If I take something close to 6, but approaching from the left, so slightly less than 6, when I subtract 6, I'm going to get a negative. So the left-hand limit is negative infinity. The limit as x approaches 6 from the right of 3x plus 1 over x minus 6. And once again, you plug in something close to 6, and you're going to get a positive. If I plug in something close to 6 in the denominator, it's going to be close to 0, but this time I'm approaching from the right, so the numbers are going to be bigger than 6, so when we subtract 6, we'll be left with a positive. Since the left and right limits don't match, that means that the limit as x approaches 6 of 3x plus 1 over x minus 6 does not exist. So the limit as x approaches 6 of 3x squared minus 17x minus 6 over x minus 6 squared does not exist also. Okay. All right. Okay, let's go ahead and take a look at this graphing one. Sketch a graph of a function that satisfies the following. Okay, so I'm going to start with some axes, and what I'm going to do is I'm just going to put in, the relevant information as I go. Okay, so for this first piece, I'm looking at the limit as x approaches negative 4 from the left. So I'll throw a negative 4 in my graph. As I approach from the left, it's going to be a negative 5. So I'm going to put an open circle here. Maybe I'll fill that in later, I don't know, but I'm going to always leave my limits as open circles. Next, as x approaches negative 4 from the right, we get negative 1. Okay. And f of negative 4 is positive 2. Okay, so it turns out I can't have either of these filled in because then I would not have a function. All right, next, f of 0 is 3. Now we have a limit as x approaches 3, so that's an x value of 3, and that limit is 7. This doesn't specify left or right, which means it's both sides. Okay. F of 3 is 0. So once again, this has to be an open dot. If it was filled in, I wouldn't have a function. And finally, as x approaches 5, I get not just a vertical asymptote, but it says it's going off to infinity. Okay. So at this point, if I want to fill in some of the pieces, I can do so. this particular problem didn't really require me to, because it doesn't have any special requirements like the domain is all real numbers or anything like that, but maybe feels a little bit more complete to see everything on there. Okay, so that's an example of a function that satisfies all of these requirements. All right, determine if the function is continuous at x equals 3. Remember that to be continuous at a point, that we need three things. F of 3 exists. The limit as x approaches 3 of f of x exists. And then we need those two things that we just found to actually equal each other. Okay, so let's deal with these one at a time. What is f of 3, right? To show something exists, the easiest way is to actually find it, right? So when x is 3, my function is -1. Okay, now let's see. Okay, so the first one checks out. Now let's see if the limit exists. The limit is a little bit difficult. What I need to do is look at the left and right limits, because I can't write down a function just for f of x. This is piecewise. But if I look at a limit as x approaches 3 from the left of f of x, if I'm approaching 3 from the left, that means that my x values are less than 3. And when x is less than 3, I have a formula for my function. And that's 5 minus 2x. And now I can solve this limit using direct substitution. So I get 5 minus 6, or -1. Okay. Now let's look at the limit as x approaches 3 from the right. As x approaches 3 from the right, the x values are bigger than 3. So according to my piecewise function, the formula is x minus 1 squared. Okay. So I can solve this limit using direct substitution. So I get 3 minus 1 squared, which is 2 squared, or 4. Okay. Since the left and right limits don't match, the limit as x approaches 3 of f of x does not exist. And I can stop there, right? Because now that I have one that doesn't work, I know that this cannot be continuous at x equals 3. Emma, you have a question?
Yes, so I solved the problem by graphing it out. Is that okay?
Yeah.
Thank you.
Right, so if you graphed this at 3, we have -1, and then 5 minus 2x. You probably need to, compute an endpoint, but look at that negative slope. Okay, and then x minus 1 squared, that's x squared shifted to the right by 1. So like that. And then, yeah, you can look at that graph and say, yeah, here at 3, it's not continuous. I got to jump. Okay, this one we can't graph because I don't know a value for a and b, so I don't know what the formula is for graphing it. Find the values of a and b that will make the following function continuous. Now, I know that lines are continuous on their domains. Square root functions are continuous on their domains. The only place where this function can have a problem is at these places where it switches formulas, right? It could have a jump. So what I want to do is I want to look at x equals -1, and I want to look at x equals 3 and see what information I get from those two. Okay, and in this case, I want it to be continuous, so I want that limit from the left equals the limit from the right, so the limit exists and equals the function value. Okay, so let's look at the limit as x approaches -1 from the left. That's equal to the limit as x approaches -1 from the left of square root of ax squared. And I'm going to solve this limit using direct substitution. X is approaching -1, so I replace my x with a -1. -1 squared is 1, so this is just square root of a. Okay. Now let's look at the limit as x approaches -1 from the right. As x approaches -1 from the right, I want x values bigger than -1. Now 3 is bigger than -1, but with a limit, we're thinking about what happens as we get infinitely close. So I want to be bigger than -1, but very close to -1. Okay, so that's going to be, from -1 to 3 here. So it's going to be the ax plus b formula. And when I use direct substitution, I replace the x with a -1, so I get -a plus b. To be continuous, I need the limit from the left and the limit from the right to match. So we need square root of a to be equal to -a plus b. That gives us an equation to work with to find a and b, but one equation is not enough to find two numbers. So now we're going to switch over and look at what happens at x equals 3. Same setup, I want to look at the limit as x approaches 3 from the left. As I approach 3 from the left, my formula is ax plus b. When I use direct substitution, I replace the x with the 3, so I get 3a plus b. Now let's look at the limit as x approaches 3 from the right. Since my x values will be bigger than 3, the formula is bx plus 2. So I'll replace the x with a 3, so we'll get 3b plus 2. And once again, I want the limit from the left and right to match in order to make it continuous. So we need that 3a plus b is equal to 3b plus 2. So I have two equations now and two unknowns. So I'm going to solve this system. I'm just going to, solve for either a or b in one equation and plug into the other. This one has square roots involved, so I want to maybe hold off on that one. That's going to be more complicated, so I'll wait on that. So let's solve this equation, and I can solve for either a or b. If I solve for b, I only have to replace in one spot, and it's not the square root. So I feel like solving for b is the way to go here. So I'm going to subtract b from both sides, and then subtract 2 from both sides. So we have 3a minus 2 equals 2b. And then divide both sides by 2. So 3 halves a minus 1 equals b. So I'm going to plug this expression in for b. So now I have the square root of a equals the opposite of a plus 3 halves a minus 1. 3 halves a minus a is 1/2 of a. Okay. And you can either leave it as fractions here, or if you want, you can multiply both sides by 2 to eliminate the fractions entirely. You don't have to do that, but if you don't like having fractions, then that's kind of the way to go. All right, now because I have a square root involved, I need to get rid of that square root. So what I'm going to do is I'm going to square both sides. Okay, and be careful of my handwriting. That's an A, not a 9. Okay, on the left when I square it, 2 squared is 4. Square root of a squared is going to give me an a. On the right, I'm going to FOIL that out, so I'm going to get a squared minus 4a plus 4. So now I have what looks like a quadratic. I'll subtract 4a from both sides. Okay. And now, if this factors nicely, I can factor it. I think in this case, though, we're out of luck. I don't think that this is going to end up factoring nicely. So I'm going to use the quadratic formula. So I get that a is the opposite of -8. So 8 plus or minus the square root of -8 squared minus 4 times 1 times 4 all over 2 times 1. So -8 squared is a positive 64 minus 16. Okay, so 64 minus 16 is 48. So the square root of 48. Okay. Now at this point, you would be completely forgiven if you just switch over to decimals. We could do this in the way that I think that maybe you'd be used to, from your days in like algebra and pre-calculus, where we say, okay, I have a square root of 48. Can I pull stuff out of that? To make it the square root of something smaller. Okay. So 48 is like a 16 times 3. Write this maybe off to the side. So if I take the square root of 48, that's the square root of 16 times the square root of 3, and the square root of 16 is 4. Okay, so square root of 48 is 4 root 3. So I'd have 8 plus 4 root 3 over 2, and I would have 8 minus 4 root 3 over 2. Okay, and when I divide by 2, I'm going to get 4 plus 2 root 3 and 4 minus 2 root 3. Okay, now just double checking here. 4 minus 2 times the square root of 3. Oh, and my calculator is 0.53. Okay, so I want to make sure that both of these a values actually solve my my equation, my original equation back here. Right, this is the equation I wanted to solve. And one of the dangers is anytime you square both sides of an equation, you have the possibility of introducing a fake solution. So what I'm going to do is I'm going to, here, I'll put my calculator up on the screen. If I can find my mouse. Okay. And I'm going to check both of these numbers, right? So if I take 4 plus 2 root 3, right, I get some number. Let's try that, right? So what happens when I plug that on the left? I get the square root of that a value. And what happens when I plug that in on the right? If I take 1/2 of that a value minus 1, I get the same thing. So that solution works. Okay, good. Now let's try the other one. Let's try 4 minus 2 root 3. Okay, so I'm going to take the square root of a, get some number, and then I'm going to take 1/2 of a minus 1. And I don't get the same answer, right? This one is negative, and so I don't get the same thing on both sides, so this isn't a real solution. Now you can see that if you were to square both sides, they would look the same, and that's where that fake solution came in from. Okay, so this one is not a real solution. All right. So I have one solution for A, and now I compute for B. B is 3/2 of A minus 1. So 3/2 times 4 is 6. 3/2 times 2 root 3 is 3 root 3. So I have 3 root 3 plus 5. All right, this one was a little on the complicated side. Any questions on this one? Okay, well, let's plot on along. I think we did this one in class, but I don't know, maybe for completeness of the video, we'll just kind of do them all. Use the intermediate value theorem to show that this expression has a root in the interval 0 to 2. So I'm going to start by saying let f of x equal x cubed plus x minus 3. Note that f is a polynomial. So f is continuous. That's an important thing to note because in order to use the intermediate value theorem, I need to have a continuous function. Okay. All right, so now let's compute what is f of 0. F of 0 is 0 cubed plus 0 minus 3, which is negative 3. F of 2 is 2 cubed plus 2 minus 3, which is 7. Okay, so since 0 is between f of 0 equals negative 3 and f of 2 equals 7, then by the intermediate value theorem, there is a number c in the interval 0 to 2 with f of c equals 0. Okay. Then c is a root of x cubed plus x minus 3 in the interval 0 to 2. And we're done. Okay, so I went through that one maybe a little bit quickly, but we did do that in class. So this is sort of our second time around. Okay, epsilon delta definitions of a limit. So I like to break these into two parts. The first one is where we're trying to find delta. So I work backwards there. We say, okay, I want to start with the absolute value of f of x minus L less than epsilon and work towards x minus a less than delta. In this case, the a is 3, so I'm working towards x minus 3 less than delta. The f of x is 6x minus 3. The L is 15. Okay, so 6x minus 3 minus 15 is 6x minus 18. Since I'm working towards an x minus 3 and I have a 6x, I'm going to factor out a 6. And then if I divide both sides by 6, I will have that x minus 3 is less than epsilon over 6. Okay, and so if I want x minus 3 to be less than delta, and I have an epsilon over 6 here, then we're going to pick delta equals epsilon over 6. Okay, this was backwards. I'm starting with what I wanted to conclude. So the proper direction from the logic side is for any number epsilon greater than 0, let delta, right, for any epsilon, we pick the delta. We're going to let the delta equal epsilon over 6. Then if 0 is less than x minus 3 is less than delta, then that implies that x minus 3 is less than epsilon over 6, which, using our work to the left over here, following it backwards, means that f of x minus L is less than epsilon. And we're done. We never used the 0 less than absolute x minus 3 part. That does come up in the homework, though. In the second homework problem, I think it's question 8, you have to cancel some terms. And if I wanted to cancel, let's suppose I had like an x minus 2 term to cancel. I guess it would be an x minus 3 term to cancel. I can only do that if x is not equal to 3. And so I would go over here and say, oh, okay, because 0 is less than absolute x minus 3, x is not equal to 3. So then I can do that canceling. Okay, let's do another one of these. So first we work backwards, start with f of x minus L less than epsilon, and work towards x minus a less than delta. Here my a is 7. The f of x is 9 minus x. The L is 2. 9 minus 2 is 7. So this is 7 minus x less than epsilon. I have a 7 minus x. I want an x minus 7, so we're going to factor out a negative 1. However, the absolute value of negative 1 is just 1. So this is exactly the same as x minus 7 in absolute values. So here we can pick delta equals epsilon. Okay, so for any number epsilon greater than 0, let delta equal epsilon. Then if 0 is less than x minus 7 is less than delta, that implies that x minus 7 is less than epsilon. And then following my logic backwards, that means that f of x minus L is less than epsilon. So that gives me that the limit as x approaches 7 of my f of x is equal to L. Okay, I don't think I wrote that in the last one. It's kind of nice to put that very last statement on there. Feels like it really caps things off. So the limit as x approaches a of the f of x that we used is equal to the L. Okay. Okay, a couple more limits. These are tricky. It's not just a factor and cancel situation. If I try direct substitution, we'll have 3 times 4 plus 2 over 4 plus 3 minus 2 all over 4 minus 4. That denominator is definitely 0. Let's see what's going on in the numerator. 3 times 4 is 12, plus 2 is 14 over 7 minus 2. 14 over 7 is 2. 2 minus 2 is 0. Okay. So I have a 0 over 0 situation, but it's not a polynomial, so I'm not going to be able to factor. I have to do something else. So here's what we're going to do. I have this 3x plus 2 over x plus 3, and I'm subtracting 2. I'm going to turn this into a fraction. The way that I'm going to do that is I'm going to multiply and divide by x plus 3 so that I have a common denominator. Okay. One of the things that I like to do if I'm subtracting a fraction is to not subtract. I really prefer to add a negative number. And the reason that I do that is because then I'm less likely to lose a negative. I like to have habits that prevent me from making simple mistakes because it's, how do you prevent simple mistakes, right? How do you prevent, adding wrong or something like that? You usually can't, you just have to be careful. But if you can create habits that point these things out to your attention, then you're less likely to make the mistake. So don't subtract fractions, add a negative fraction. Okay, so now we have the same denominator, x plus 3. So on the left, I have x plus 2. On the right, I have negative 2 times x plus 3. So if I just distribute, I'll have negative 2x minus 6. Okay, if I left that as just a subtracting 2, it's just very likely that I would get a negative 2x, but a plus 6. It's just a really common mistake that people make. Okay, instead of dividing by x minus 4, I'm going to multiply by 1 over x minus 4. Because I know dividing by a fraction is the same as multiplying by its reciprocal. You can think of that as being x minus 4 over 1. And that way I only have like one layer of fractions. I don't have fractions within fractions. Okay, in that denominator, I like to leave things as they are. It's already a nice factored form. There's no reason to change that. In the numerator, let's just clean things up. 3x minus 2x gives me x. 2 minus 6 is a negative 4. And now I can cancel that x minus 4 in the numerator with the x minus 4 in the denominator because we're working inside a limit. So this is equal to the new limit where we have 1 over x plus 3. And now we use direct substitution and we get 1 over 4 plus 3, which is 1/7. So the limit as x approaches 4 of 3x plus 2 over x plus 3 minus 2 all over x minus 4 is equal to 1/7. Okay, so if you have fractions within a fraction, get a common denominator. All right, for this last one, I think it's the last problem. No, there's 2 more. Okay, for this second to last one, what I need to do is, again, I don't have a polynomial on top. We'll start by trying direct substitution. Hopefully it works, but I don't really think so. So we have 10 minus 2 times negative 3 minus 4 all over negative 3 plus 3. Okay, minus a negative is plus, so I have 10 plus 6, so the square root of 16. Square root of 16 is 4, minus 4 is 0, so we have 0 over 0. Just like the last problem, though, it's not a polynomial, so I can't factor it. So what we're going to do instead is say that this is equal to this new limit, and I'm going to rationalize the numerator by multiplying by a conjugate. So I'm going to take this fraction and multiply it by the same thing I have on top, except instead of separated with a subtract, I will separate it with plus. That's the conjugate. And to make sure that I haven't changed the value of the limit I'm working with, I divide by the same thing, so I'm really just multiplying by a fancy form of 1. Okay. In the numerator, let's multiply things out. The square root times itself, the square root will go away. Then I have plus 4 of these square roots, minus 4 of those square roots, those add to 0. And then negative 4 times positive 4 is negative 16. In the denominator, I do not want to multiply stuff out. I don't have any good reason to, and in fact, I have good reason not to. I have a 0 in the denominator. That's coming from this x plus 3 factor. I'd really like to cancel that factor. Since it's a nice factor, it's easy to cancel. If I FOIL things out, then it's hard to figure out what to do. So leave that denominator factored out. All right, so let's simplify the numerator a little bit more. The negative 2x is just a negative 2x. 10 minus 16 is a negative 6. So a lot of rewriting. I want to cancel an x plus 3, and in the numerator, if I factor out a negative 2, I think that I will be able to do that. So we factor out the negative 2, and we're left with x plus 3 in the numerator. So I'm just going to copy down this denominator for a second. And now my x plus 3 factors will cancel. And now we can use direct substitution. So we have negative 2 on top. In the denominator, we have the square root of 10 minus 2 times negative 3, and then plus 4. Negative 2 times negative 3 is a positive 6. 10 plus 6 is 16. Square root of 16 is 4. 4 plus 4 is 8, so I have negative 2/8, which is a negative 1. So the limit as x approaches negative 3 of the square root of 10 minus 2x minus 4 all over x plus 3 is equal to negative 1/4.
I have a question.
Yeah.
So for this one and the one before, I like didn't know how to like get anything rid of it, so I just chose like, a number close like above and below, like coming from the left and the right, and then like I got the same thing just in decimal form. Would that be fine or
No, so with this one, that's when the directions say find it analytically, that's where we want to be using the algebra to find it, not plugging in numbers. So you can do that to check to see that your answer is correct, but you want to show this using algebra. And
okay.
and there is a reason for that. When we finish the exam, when we start chapter 3, we're going to do something like this again, except our answer may not be a number, it might be like an expression, right? So it might have like, variables in it. And of course you can't do that on a calculator. So that's why we're sort of going through this extra effort.
Okay.
All right, so let's find this last one. It's a limit. I'm always going to start by trying direct substitution. So we have 4 minus 2 over 2 squared minus 4. 4 minus 2 is 2. 4 minus 4 is 0. Non-zero number over 0 tells me I have an infinite limit. Okay, so we have one more infinite limit on here. You don't have to, but I like to factor if it's possible, even if the factors aren't going anywhere. So in the denominator, I'd have x plus 2 times x minus 2. So nothing cancels, okay? But now when I check my left and right limits, it's sort of easier to see what's going on. When I plug in something close to 2, 4 minus about 2 is going to give me about 2, which is positive. If I plug in something close to 2, 2 plus 2 is about 4, so that's a positive. 2 minus 2 is about 0, but if I'm approaching from the left, I'm looking at less than 2, so when I subtract 2, I get negative. So this is a negative infinity. So now let's look at the limit as x approaches 2 from the right of 4 minus x over x plus 2 times x minus 2. And we have a similar situation when x is near 2. 4 minus something close to 2 is going to be about 2, which is positive. 2 plus 2 is 4, so this one's positive. Here I'm close to 0, but if I'm looking at numbers that are slightly bigger than 2, when I subtract 2, I'll be left with a positive. So this is going to give me a positive infinity, and these two don't match. So since the left and right limits don't match, the original limit does not exist. All right. Any other questions? Any questions that over the exam?